Section 3.3, Differentiation Rules. We learned how to find derivatives at particular points using the limit definition. We also learned how to find derivative functions for any point in the function's domain, again using the limit definition. And each time we calculate these limits, we get a little bit frustrated because of the indeterminate forms and the algebra mistakes that we make, but I've got great news for you. In this section, we're going to use those cumbersome limit definitions to find shortcuts. Now we can't find the shortcuts without knowing the limit definition, which is why we've done that up until now. But once we learn these shortcuts, we can stop using those limits of the difference quotients and we can start using the differentiation rules. Let's start by looking at a constant function. F of x is equal to 8. And let's try to find the derivative for this type of function. Remember that the derivative function is the limit of the difference quotient. So that's exactly what we're going to do, where the function that we're using to calculate the difference quotient is the constant 8. So what is f of x plus h for our function? Well, our function is a constant. It doesn't care what x is. It doesn't care what h is. It's just 8 all the time. So when we go to write our difference quotient, we're going to have 8 where the f of x plus h goes. We're going to have 8 where the f of x goes. And then we'll have h in the bottom. And then we notice that the numerator, 8 minus 8, that's just 0. And before we think about the limit, put the limit part on hold for a moment, let's focus in on 0 divided by h. If h is equal to 0, then we are out of luck. But as long as h is not equal to 0, then 0 divided by h is equal to 0. Think about 0 divided by 5, that's 0. 0 divided by 11, that's 0. Any number in the denominator is fine as long as it's not 0. We're not allowed to divide by 0. So if I simplify what's in this box before trying to apply the limit, instead of 0 over h, I'm really taking the limit of 0. And if h is approaching 0 for a constant, 0, that's just equal to 0 as well. So this basic rule says that if I'm looking at a function that's equal to a constant like 8, the derivative function is equal to 0. Let's try and generalize that. Instead of talking about a fixed number, 8, let's use c as like a placeholder for any constant. It could be positive numbers, negative numbers, fractions, decimals, irrationals, you name it. If I apply the same limit definition for a derivative, I can calculate the derivative function for this constant f of x equals c. So again, f with x plus h plugged into it for a constant is just the constant. And same with f with x plugged into it, just a constant. Since c minus c is 0, we're really looking at 0 divided by h. But 0 divided by any number other than 0 is 0. So we're really looking at the limit of a constant, and we know one of our basic facts, limits of constants are just equal to the constant. So we've just come up with one of our basic rules, which says for any function equal to a constant, the derivative is 0. This is one of our shortcuts. If I ask you, find the derivative for the function f of x equals 11, you literally don't have to do any work. Once you notice that your function is a plain old constant, you say, oh, derivative? Sure, that's equal to 0. Doesn't matter if the original function was equal to a positive or a negative number. You see that it's a constant, and you say, awesome, derivative equal to 0. Could have been a fraction. Derivative is still equal to 0. It can be 0 itself. Derivative still equal to 0. So what all of these functions have in common is that there's no variable in the original function definition. It's simply a constant. And if a derivative measures the way things are changing, then we expect the derivative to be equal to 0 for any constant function. Let's look at a basic polynomial like x cubed. If we want to find the derivative for x cubed, then we'll start with our limit definition of a derivative. So we need f of x plus h, which would look like x plus h cubed. And let's take a second to talk about how to multiply this out. We can use something called the Binomial Theorem, which takes any binomial raised to the nth power, and it follows this pattern. Basically, the pattern is this. Every term has a factor of x, h, and a coefficient. The first coefficient on the first term doesn't really show up because it's just a 1. The next coefficient is an n. The next coefficient is calculated using something called combinations. The next coefficient is also calculated using combinations. There's a big gap here since we don't know how many terms there are. We're just following the pattern, and then our last coefficients are n and then 1. If you're curious about how to calculate those coefficients, you can use something called Pascal's triangle. And I won't continue it all the way through, but the rule is that you start with a triangle of ones, so 1, 1, 1, and then you add the two terms above it to get the term below. So 2 comes from adding 1 and 1, and then all along the diagonals you'll keep the pattern of ones. The next part of the pattern is the exponents on the x terms. We start with x to the n, then we drop down 1, then we drop down 2, then we drop down 3, and we keep decreasing until we get down to x to the first power. So n minus 1. And then the pattern for h is that it starts at 0, so we have like h to the 0 power, and it increases by 1, h to the first power, h squared, h cubed, and it goes all the way up until we get to h to the nth power. So we can use this as a pattern for multiplying out binomials. In the case of x cubed, it's not so crucial that we use this shortcut pattern, but when we look at the next example, we'll need it. So let's multiply this out using our pattern. If it's x plus h cubed, that would look like x cubed plus 3 times x squared times h plus 3 times x times h squared plus h cubed. So that would be the f of x plus h. Let's go ahead and fill that into our limit definition for the derivative. Then we'll subtract off the original function, which was x cubed, and divide that by h, finishing our limit definition of the derivative. Then we'll simplify the best we can. I see a minus x cubed and a positive x cubed, so we can get rid of those. I'm just going to erase them. Then I noticed that if I tried to if I tried to direct substitution hn, I would end up with 0 on top, 0 on bottom. So I'm going to factor in h out so that I can divide h off. That would leave behind 3x squared plus 3x plus h squared, and we're going to allow the limit for h to go to 0. So anything with an h in it would become 0. So I'll have 3x squared plus 3 times x times 0 plus 0 squared. And that simplifies to 3x squared. So we can find derivatives of polynomials using this limit definition of a derivative. But actually, there's a shortcut. And that was the reason why I showed you this big old binomial piece. So let's get to that part. If I want to generalize this and talk about any polynomial, x to whatever exponent you can think of, as long as it's an integer, then I can generalize this and look for a pattern. So let's go ahead and do that. If we have f of x plus h, then that is x plus h to the nth power, which we said we had a pattern for. And if I'm going to try and do this without making too much of a mess, notice that in our numerator we have that long binomial thing, and then we're going to subtract f of x. So we're going to subtract x to the n. That's going to remove that first term. So when we write our limit definition, f of x plus h is all of this. And when we subtract f of x, it gets rid of this x to the nth term. So then we're just left with n times x to the n minus 1 times h plus n choose 3, x to the n minus 2 times h squared plus all of the terms until we get down to h to the n. Notice that everything that's left in the numerator has a factor of h in it. So I can divide that off with our denominator to get rid of the indeterminate form, reducing each of our exponents by 1. And now notice that every term in my numerator, except for this first term, has an h in it. So the second term has one factor of h, the next one, well, there's a bunch in between here with these 3 dots, and then even the last ones have factors of h's. So when we plug h in, all of those terms go to 0. And the only thing we're left with is that very first term, n times x to the n minus 1. Now this is really powerful. Let's take a moment to appreciate what we just found. If we're starting off with any generic polynomial function, x to the nth power, we just found that the derivative, f prime, will always follow the pattern n times x to the n minus 1. Now, if we want to, we can try and find a pattern here. Or we can just apply the definition directly. I like to look at it as a pattern. If the original exponent is n, then that's the new coefficient on my derivative function. And then my exponent on the derivative function is 1 less than it used to be. So let's try a couple of examples. Let's say my original function was x to the 5th power. Well, I don't have to do the limit definition anymore. I can just use this shortcut that says 5, the old exponent, now becomes the coefficient on x. And then the old exponent, 5, gets decreased by 1. So my derivative function is actually 5 times x to the 4th power. Way faster than what we had to do to find the limit before. What about if I have x to the 100th power? Not a problem. Derivative, follow the pattern. The exponent on the original function is 100, so that becomes my coefficient. And then I decrease that by 1 to make the new exponent 99. We did calculate the derivative function for x cubed using the limit definition. Now let's do it using our shortcut. 3 was the old exponent, now that's the coefficient. 3 minus 1 is 2. That's the new exponent. So we can quickly calculate the derivative for any polynomial function. All we have to do is identify what the exponent is and bring it on down. So just to summarize, we've talked about two basic rules. The first rule we talked about is that the derivative of a constant is always equal to 0. The second rule we talked about is the derivative of a polynomial term, like x to the n, follows the pattern n times x to the n minus 1. It's almost like you're taking that exponent n and bringing it down as a new coefficient so that you have n, x, and then n minus 1.